Good morning. This is Adam Wise of Andor Technology, an Oxford Instruments company. And in this short demo, I'll show you how to capture high-speed spectra on a Marana 4BV11 SCMOS camera. On my screen, you can see an image of a multicolored LED source, imaged through a diffraction grating. I have the source cycling every millisecond between blue, green, and red emission, but because the exposure time here, about 30 milliseconds, is long relative to the emission of any one channel, it's all mixed together. So if I view this and I look at it as a spectrum, you can see I've got a lot going on here. I want to separate the individual channels out rather than have them all mushed together in time. Here I've got my blue, green, and red channels overlapping, and here I have the second order diffraction pattern. But I want to be able to catch individual frames or individual channels, and I'll show you how to do that. So first you'll see, I'm going to go back to an image view here. This is the whole chip being imaged right now, all 4 megapixels. So if I go to the highest frame rate that I can get, it's about 47 frames per second. It's in the fastest frame rate mode right now, 12-bit, which is fine. Unfortunately, that's not going to be fast enough to keep up with my spectra, which are being generated at about 500 hertz, although I can turn that up, and I'll do that at the end of the demonstration, I think. But my question is first, how do I get that frame rate higher? Well, I can definitely get that frame rate higher. This is the fastest full frame rate in this sensitivity dynamic range mode. I can get the frame rate higher by reading out fewer rows. So if I go to binning and ROI, I can drop the height of this. The question is, where do I actually want to capture rows? I'm going to zoom in my image here. And it's going from about y equals 1220 to y equals 1360. That's in pixel numbers, with 0 being at the bottom, 2048 being at the top. But say I want to capture the main area here. That'd be about 1280 to 1320. So I'm going to put the bottom, or the height at, say, 40 pixels, the bottom at 1280. And I'm going to take another exposure in image mode just to make sure that I have the right part of the chip being captured. Zoom in here. That looks okay. So just to increase the signal to noise, what I'm going to do is to vertically bin all of these pixels. So I'm going to kind of squeeze this spectrum that has a vertical extent, this image that has a vertical extent, into a single spectrum. So basically just sum along the columns. And I can do that by making my vertical binning here 40. Now when I take data, it's going to come out as a spectra. I'm going to switch this from image to spectra view. And I could even do peak labeling too if I wanted to, but I'm going to leave that as just regular 2D for now. So I've got my blue channel, my green channel squeezed in there, my red channel in the first order, as well as my second order out here. And they're all pressed together. So what I need to do is I need to increase the frame rate. So now the question is, what is my max frame rate now that I've dropped to 40 rows? I'll increase my frame rate here, see how high I can get. And I can go up to 2 kilohertz at this point, which is great. That's going to be more than enough speed. Of course, that will drop a little bit when I switch triggering modes. Right now, I'm freely triggering. I'm letting the camera decide when to take the next acquisition. If I do this live, you can see in my oscilloscope, the fire signals are kind of coming in whenever. There's no synchronization. What I'm going to need to do to capture these spectra efficiently is to synchronize my camera with my light source. So I'm going to switch this to external. So external triggering will be when the camera is ready and a trigger comes in, it will take an exposure and then repeat the cycle as long as my measurements are still going. I want to make sure I'm monitoring the right signal. So blue is the signal from the camera right now, the auxiliary I/O port. I'm going to go to auxiliary output configuration. Fire all is perfectly fine. So this is fire any was what I'd like to see. So I want to see when this chip is exposing. When any of the rows are being exposed. I could do fire row 1. I have a whole video that I'll try to link to here on this auxiliary I/O port, and you can look into that for more information about this mode. But I'll do fire any for now. I want to see when the chip, any part of the chip is photosensitive. So if I run this now, and I'm just going to run it live. So you can see now my fire signal, this is when the chip is photosensitive, is now locked to the actual trigger. So I'm actually getting individual channels now. So what would I like to do next? Well, why not put a wavelength axis on there? So I'll do another long. Oh, this exposure time is quite low. I can set this to relatively low. I can set this to one millisecond. It should be perfectly fine. Yeah, it still works perfectly well. So I'm gonna switch this back to a longer exposure, 100 milliseconds. Oop, saturating here, and that's all right. I'll do a short exposure, 50 milliseconds. That's still saturating. So now I have my channels visible. So I'm just going to put in a very quick rough and ready calibration here using the manual x-axis calibration tool. So I'm going to go to calibrate, manual x calibration, and then I'll put in a couple of values for pixels that will be used to extrapolate an x-axis using a polynomial fitting function. So what I'm going to do is basically just create a lookup table that'll say this pixel is this wavelength, this pixel is this wavelength, this pixel is this wavelength. And then Solace will use a polynomial fitting function of my choice to generate the rest of the axis. So I'm going to capture that pixel, and I'm going to add the nominal value for it, which would be 480. Then I'm going to put in the next one. This is my red channel, which should be about 640 nanometers. Then I'll use the second order of the blue channel. Then that pixel should show up around 960. That's twice the wavelength of this for the second order. And I have a quadratic function selected. Here I'll choose to apply the calibration to the current data and new acquisitions. And now I have a rough and ready x-axis calibration. If I were doing this for high precision, I would use a calibration lamp that had much more precise lines. But I just want to make it clearer which channel is which when I zoom in a little more on the first order here. So now I want to record a movie to make sure I'm getting, that I can record these frames as they come in. I'm going to go to a kinetic series. I'll do a series of, say, 1,000 frames. And then I'll take data. Oh, and I forgot to reduce my exposure time. I'm going to change that back down to one millisecond. So I could also set up a different mode for triggering, which would use the trigger as the to control the exposure time. And I'll show that later, but for the moment, I just want to have a set exposure time. Let's make sure this is still working all right. And you can see that, that was 100 frames or 1,000 frames were over quite quickly at about a little less than a kilohertz. But I could do a longer one just to show you on the oscilloscope that the exposure and the fire signal were matching. So here's my signal from the light when the light is on, and here's my entire chip being photosensitive. Now you might ask why, if my exposure time is 1 millisecond, is this longer? And I'm going to go into that a little bit later when we talk more about the specifics of rolling shutter exposure and readout. But for the moment, I'll go through my data again when this is complete. And you can see that I'm able to discern individual channels in the light source turning on and off with time. So I'm going to change the auto scale here on the data, rescale it to the brightest channel. This is my blue channel right here, which is the brightest on the LED source. Then skip ahead to the next exposure. Oop. So I have blue, red, green, 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 over and over and over again. So I'm able to demix the temporarily mixed up spectrum that I had in the first one by doing high-speed spectroscopy using this camera. So I can push this even further for the, I won't do that for the moment, but I could push this even further in time, and perhaps I will in a different video to show the extreme high-speed aspects. So this is just below a kilohertz for the moment. Anyway, if you have questions about high-speed spectroscopy, feel free to give me an email at a.wise@andor.com or visit the Andor website for more information. And otherwise, have a good rest of your day.